Okay, we are now recording. Let's go from current slide, but we're not quite there yet. Let's go from current slide. There we go. All right. Now, so did I talk about Blackboard last time? I had everything loaded? I did. Okay, well, just to let you know then. When you go to the home page of Blackboard for this course, you'll see a series of tabs here on the left-hand side of the screen. And they're in sort of groups, 6, 7, 8, whatever, groups of those numbers. In the first group, right about the middle, you'll see one that says syllabus and book information. Okay? That's there. It's been updated. It is current. And anyone can go out there and print off that acknowledgement page or send it, email it to me, whatever you want to do with that. Okay? So that's there. Okay? Now, you can also hear me talk about it. We'll get to that later. Right below that tab is one that says instructor and office hours, or instructor information and office hours, or something like that. That's where my locator card is. That shows when I'm on campus, when I'm off campus, which campus I'm on, when I'm in class, out of class, lunch, whatever. Don't worry about the lunch part because I usually eat in my office. I bring my lunch, I eat in my office, so you can come by during then too if you don't mind watching me chew and food fall out of my mouth. Okay, that kind of stuff. So that's there. Get down to the next group, and I think it's about third from the last in that group. There's a tab that says handouts, PPTs, and more, or something like that. Now, in that group, you'll find the research paper instructions. There is a research paper. You can go and read the instructions there. It's been updated. Everything should be correct on that. After that, I don't know if I've got the order right here, but I have every PowerPoint we could possibly do in this class. Every section's PowerPoint, and it goes by section, starting with 1.4, 1.5, blah, blah, blah. Okay? Now, somewhere there, you'll then see a tab that says Math 112 YouTube videos. And if you go to that video, to that tab, and click on it, you're going to see a whole laundry list of videos. I'm going to guess about 30 or so, maybe more, okay? Now, unfortunately, the ones at the top are old videos. Not that they're bad videos, but they're older ones. The ones at the bottoms are the current ones, okay? However, get your name, please. Second. Oh, Jacoria, got it. I marked you here earlier. I was psychic. I knew you were going to come. Okay. So, there we go. All right. And the reason I leave the old ones up there, it happened this week. I was teaching a class. One of those storms started to come up, knocked the power off. When the power's off, I can't record. Okay? So therefore, I keep the old recordings there just in case something happens and I can't record a class. I'll have the previously recorded class up there. So, if you go down to the bottom, the first video says syllabus. The first one that's from this term says syllabus. That's how you can tell where the term began. When you go to that, you'll hear all sorts of stuff. Can I get your name, please? Number what? Okay. There, okay, got it. Okay. My hearing's so bad. Okay. Good deal. Now, that first one down there, you'll hear me start talking about all sorts of stuff, including the syllabus. I don't even think we got through the syllabus because that first day was horrendous about everything not working. They hadn't put the new projector in here. I had to check one out of the library. It was just a mess. Okay, so we started talking about the syllabus. On the next day, that one I think says research or something like that, we finished the syllabus, talked about the research paper, talked about so everything that you saw earlier, research paper instructions, the syllabus up here, locator card, you'll hear me talk about on those videos. So you can have an active version or a passive version, whichever you want. And then we still didn't get to any math, because last time, even with the new projector, it would work, okay? And I had some magic students here who got it to work while I went down to it. And is it Charles? Oh, you poor guy. Okay, no, I say that every time. Okay. All right. I know you're in. There you are. Okay. So there's that. And then after all those tabs, there's also some links to some websites that either I have found or students have told me they like. They have them in the course, so I put those links there too at the end of that. Handouts, PPTs, and more. That's the more part. Okay. All right, that's all there. Now we got everything preliminary done except for one thing. Safety. Okay, now we're not going to be doing anything dangerous in here, so there's not that kind, but there are safety issues you always ought to have in the front of your mind, or somewhere in your mind, lost in your mind. And your name, please? Huh?
We hunt.
Yeah, got it. Tyler, right? Yeah. Okay. All right. Now, three areas of safety we have to keep in mind. Anyone think of any one of them? Say again? Fire, exactly. Let's take worst case scenario. My computer blows up and sets my book on fire and the stand here on fire. What do we do? Say again? Leave. All right. Yes, let's leave the room, leave the building, let it burn, and don't tell anybody else. Okay? That's a wonderful idea, sort of. What else might we want to do before we leave?
Sound the alarm.
Say again?
Sound the alarm.
Sound the alarm. Okay, where is the closest fire alarm?
In the hallway.
In the hallway. Oh, okay. Come on in. What's your name, please? Raquel. Okay. There you are. All right. We're just talking about safety. What if there's a fire? What if it started in here? Before we leave, we decide to sound the alarm, and someone was telling me the nearest fire alarm is out here in the hallway. Sorry, I don't see one. Where is it in the hallway?
I want to say go down towards the bathrooms.
Okay, you could go that way. Can I get your name, please?
Amber.
Amber. Okay, got it. You're the Amber that's not pink. Okay. Yeah, Amber. Is it Senior? How do you pronounce your last name? Huh? Senior? Okay, got it. All right. So I don't see a thing, even if I go toward. Okay, can I get your name, please? Amari, got it. Thank you. All right, turning into a great crowd today. Okay. Even if I go toward the bathroom down here, I don't see a fire alarm. Make sure. Nope. Not there. Okay. Hey, howdy. Not one, I got it. I pulled in another one. Okay. Haven't found the fire alarm yet, but Kiara? Is that it? Okay, is that how you pronounce it?
Yes.
Okay, good. All right. Actually, what I want you to do is visualize this building. I wish they had the evacuation plan like they do in just about every classroom. I want to go take one off the wall in the hall. But this old part of the building is like one big horseshoe. This is the long hall, and then there's a wing that goes there and a wing that goes there. You got the idea? Mm-hmm. They're all the parts that have the terrazzo floors and the tiled walls. Okay? That's the old part of the building. Built before fire alarms were code. So nowhere on this hall will you find a fire alarm. Okay? Nowhere. But if you go out of the hall here, okay, and you take a right, and there's a stairwell just part of this classroom. Go down that stairwell, half flight of stairs, into that newer area where the bookstore and cashier's windows here, the administrative offices are here. Go toward the administrative offices. That's the newest part of the building. There are fire alarms. So I was, yes. What's that? I hope not. Okay. Maybe if it took you that long to find it, we would. But no. Now that you know, somebody can go. Now what I suggest is 2 people go together. Just in case one person slips and falls, the other can still get there, okay? And then pick them up on the way back. Okay, so that's where we go.
Well, so if I make a fire alarm, I'm going out the door after I pull it, so.
Okay, yeah, I know. Well, you're not going back and pick up that port. Okay. Okay, hang it up, you're on your own. Okay, never mind. Okay. All right. So someone, in fact, I suggest 2 people go to pull a fire alarm. Good idea. Now, the suggestion of where you go afterwards, that's another good idea. Now, remember that exit I was telling you about there? I mean, the stairwell? Once you pull that alarm, go down that other half flight and head straight out of the building that way toward the hospital. Okay? Don't go all the way to the hospital, though, unless you're injured. Or you left her behind. Okay, so go out into the parking lot, at least 75 feet away from the building. You might need to go down on the grassy part to get far enough. Because if there is a fire in the building, there could be an explosion, glass could be thrown outward. You want to be outside the range of that. So, go out. Do you leave? No. Okay? Because, and we'll get to that in a minute, that's one thing to do, pull a fire alarm. What else might we do? Okay, the stuff's burning up in here. What might we do? Oh, we might want to put it out. Where is the closest fire extinguisher? Okay, now there is one down the hallway that way, but a bit closer if you go this way. Okay, to the left. At the end of the hall, you'll see it right there, smack in the wall. There's the fire extinguisher. I know some of you guys have always poked my nose and said, wouldn't it be neat to break that glass? You know? No, you didn't think that. Okay, but maybe some of you gals thought the same thing. There's your chance. Somebody go get the fire extinguisher. I will handle it if you don't feel comfortable doing it, but we'll try to put out the fire at the same time. Say what again?
I said if the computer blew up, it blew up on you, so we spraying you with it too.
Okay, well, you see, what I'm supposed to do is make myself expendable, train you in what you're supposed to do so you'll know what to do in case I'm blown up as well. Wishful thinking, though, by the way. Thank you so much. Okay. All right. I know which way your mind worked. Yeah.
To me, it don't make sense because, like, all this going on, right? All this going on.
Right.
And then we dipping, right? We all gone. And then if you in the fire, why we coming back to you? Why we can't just... Like, you caught on fire. We gotta go get the fire extinguisher.
So you don't care if the rest of the building blows up. If I'm gone, who cares about the rest of it? I like her thinking a little bit better than I do yours, but that's still.
I mean, you just gotta think, like, because it's gonna be hell of people trying to get out the door.
Okay, yeah. And we do that. And I haven't gotten to that part yet. This all is happening at the same time. So somebody went to do the fire alarm. Somebody went to get the fire extinguisher. There's one other thing we really ought to do.
Single file line out.
Oh, say again.
Single file out.
Okay, yeah, so even before that, same time, aha. Now, actually, someone said 9/11. That's a good number to call. Not the date, but the number. But there is actually a little bit better one.
Call the police.
The police, okay. The door I come in, I think every door in this building coming in from the outside has a sheet of paper on it giving the number for Bessemer Police and Birmingham Police, the campus police, our police force here. That's the best number to call because they've got direct lines to 911. They can get that word out very fast. They need to know. So I would suggest to you, now I don't bring my cell phone to class because I don't want it going off when I'm teaching. But you probably have, a few of you might have your cell phones. So that's a good number to put on speed dial in your cell phone. You know, go right to that, call campus police. If you don't have that number in there, 911 is next best. So at least one person do that, okay? So now we've taken care of preliminaries. Now we do what all of you are suggesting, get out of here. Where do we go, though, is the question. Okay? Again, we go out the door here, hang a right, go right to that first stairwell, take a right, go all the way down, and then all the way out. The front of the building toward the hospital. Okay? At least 75 feet. Go together, take it slowly. There's no reason to panic. When people panic and fall downstairs, you get a pile, nobody can get out, it's the worst case scenario, okay? You take it easy. Hey, it's not going to blow something up here, you know, even if I'm on fire like some people wish, but the situation is taken care of. Go out carefully, not super slowly, but now I'm going to be, if I can make it out, okay, the last person out. Because if somebody happened to have, that weekend before, been skiing or, whatever you do, and play basketball and sprained an ankle or something, and you're a little bit slower, I'm going to be out with the slowest person, making sure everybody goes out. And as I go, I'm picking up my roll book. Okay?
If it's not on fire.
Huh?
If it's not.
If it's not on fire, I'll be putting it out first. Okay. Now that's why I put it down here. Okay. So I take it with me, and then we're all gathered in a group out there in the parking lot. I call roll. If you have wandered off somewhere, if you, when you pulled the fire alarm, went out the next exit, no, you go out the same exit we're going to go out, and we can't account for you, your friend is writhing in anguish at the bottom of the stairs where you left her. Okay, that kind of stuff. What I do, I have to go back into the burning building and try to find anyone that's missing. So stay together as a group. Let's account for everyone, and then we wait to hear word. Don't say, hey, building's on fire, no more classes today, I'm out of here. It may be just a little bitty fire that's not going to affect. No smoke damage, we could be out, okay? We could have a fire drill. We do the same thing. Now, if it doesn't start here, we don't have to worry about those first things. We just proceed out, down, out, okay? So, that's what we do in case of fire. Take it easy, take it slow, not super slow, but don't rush. Don't compound the problem with falling downstairs and that kind of stuff. Injuring more legs than ankles. All right, that's one safety issue. Another one.
Weather.
A second. Weather, exactly. Hey, we got a hurricane coming, don't we? Hopefully it's not going to get this far, but they can happen, okay? And especially tornadoes. Okay, that really happens here. Many of you may have lived through some of those, okay? Now, what do we do if we hear that weather alarm? And I think we can hear it from here. I haven't heard one since I've been teaching in this room, because I don't teach here that often. What do we do if we hear the alarm? Okay, good question. We do almost the same thing we did if there's a fire alarm. We go out the door, hang a right, hang another right at the stairwell. We go down to the lowest level, but then rather than going out, we go in. Remember, in case of weather emergency, two things, down and interior. Go to the lowest possible level and interior, okay? Now, I wish we had the diagram here. We don't. But that's going to put us somewhere in near probably the bookstore area, that kind of area. Anywhere where you have walls relatively close together and corners. Corners are the strongest part of the room or a building, especially concrete block ones, okay? Good safe place. Walls are next. The middle of the room, maybe not as safe, but the lowest level is probably going to be okay. Stay together as a group. Again, I'm going to be the last one out, helping whoever the slowest one is out of here, because I'm probably the slowest one. Okay, so we make our way down, and we go to the interior. I have my roll book, calling roll again. If we can't account for everybody, I have to go back upstairs, looking in various places where could be debris coming in through glass and stuff like this. I don't want to have to do that, okay? So stay together and we account. When we hear the word, all's clear, go back, and we can. Now, the hall wells downstairs are probably pretty safe. Not a hall well that has outside glass like the doors there, but the hall wells that are on the interior, that's probably pretty safe because it's definitely safe, but it also has emergency lighting. Some of the rooms and stuff, like restrooms, have really close walls and corners, but no emergency lighting. And if we do have a weather emergency, there are really good odds that the power is going to go out. Okay? So, that takes care of weather emergency. There's one more I never even thought about before. Active shooter. Okay? And hopefully we will never have to think about it, but it's better to think about it now than when it happens. Okay? So what do we do? Now listen, remember, I'm hard of hearing. Okay? You'll probably hear the pop, 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 or the rat-a-tat-tat, or whatever it is that's first. Okay? What do we do? Okay, absolutely, we stay in the room. Now, this room gives me problems. And here's why. There is no lock on this door, certainly from the inside. There's no button to push on the outside. There is a keyhole on the really outside, and I have no key for this one. So I cannot lock the door. Okay? And the door opens outward. Another bad thing. It's good for exiting when you have a fire or something like that for the door to open outward. But for active shooting, that's not what you want. So, what we do if we hear that, first thing we do is what? Campus police is first choice, or 911 if you don't have that number in your phone. No. He's a nihilist here. He is trying to. Yeah. Well, if we are, we don't have to worry about it then, do we? Okay. No. Okay. So what we do, dial first. As soon as that phone call, we only need one phone call, but as soon as that phone call is made, what do we do with our little phones? Turn them off, completely off. We don't want some ringtone coming on when the guy's walking down the hall. No, we do not. Have those things off. Once that one phone call is made, turn those phones off. Okay. Now, we get very quiet. We turn off the light. We can't lock the door. So what do we do?
Move away from the door.
Move away from the door. He can fire in here. And I keep saying he because just about everyone has been a he. Been a couple of females involved with some of them, and most of the time it's been a white he too, unfortunately. So, bad news bears. Okay, so what we do, what I will be doing is taking these tables and stacking them up against the door like this to anything to retard his entrance. I'll do it as quietly as possible. What you do, get over here, because he can fire through the glass, through this thing, or even maybe through the wood. He's going to have a hard time firing through a concrete block wall, especially if he's standing over here trying to fire a powerful weapon. He's going to get more blowback on him than is going to make it through to the room. So that's where you get quiet as possible, and I'll be as quiet as possible, but I'm going to be stacking up as much as I can in front of the door, creating as big a barrier as possible. Okay? I'll do it quietly. Okay? Now, we sit it out quietly as possible. Okay? You don't have to worry about any other entrance. There isn't one. If he got into this office, that's a problem. Get in there. You can as corner as you can because he can fire through that. But hopefully that won't happen. Okay? There is another wall back there that they can get behind, but he's already there. Okay? I remember. Okay. He's fighting you up. No, I'm just kidding. All right. So, we hang there until we know from an authority figure all the coast is clear. Okay? Now, if he should make his way in, you don't be the hero. Your lives are ahead of you. Mine's mostly back there. Okay? So I've been in the military. I've been trained specifically for this, but I think I can handle as well as I can. That's why I'm putting up all the barriers I can, doing everything I can to keep them from getting in. you stay safe. Okay? You're our future. We want you around. All right. Any questions on safety? All right. That's enough, isn't it? Let's get to math. All right. Any questions on anything before we get going? All right. As I said earlier, we're starting with section 1.4. Chapter 1 is functions in their graphs. 1.1 is rectangular coordinate system. 1.2 is the graphs of equations. 1.3, linear equations in two variables. All that stuff should have been covered either in your high school background or in Math 100, Math 098, whatever you've taken before here. You should have that down. Now, if you are a little fuzzy about some of it, by all means go back and scan through, read through those sections, and if you have questions, bring them. I'd rather you get those things cleared up before we get to needing them. Okay, can I get your name, please? Okay, got it. Thank you. And this is your first time here, right? Okay. Let me take another pause and just go through quickly. Not go through everything. But everything from the class is loaded on Blackboard right now. Okay? So if you go to Blackboard, the home page for this class, you'll see a series of blue tabs on the left-hand side of that home page. And they're in groups. Okay? The first group, about midway down, or near the top somewhere, syllabus and book information. If you go there, you can see the syllabus, read it to your heart's content. Okay? The tab directly over that says instructor information and office hours. Okay? If you go to that, you see my locator card. That's when I'm on campus, off campus, in class, out of class, lunch, office hours, which campus I'm on, all that kind of stuff is on that locator card, as well as my phone number, email, and that kind of stuff. Okay? And also, office hours are on my syllabus as well. Phone number and email and that kind of stuff there too. Then you go down to the second group of tabs, and about the third from the bottom or somewhere like that, this is on the instructor side. I hope it's similar to the student side. I don't get to see the student side. There's one that says handouts, PPTs, and more. Okay? Under the first, I think the first thing there is your research paper instruction. There is a research paper in this class. The instructions are there under research paper instructions. Okay? After that, I think, are your PowerPoints for the whole term. I mean, every section PowerPoints that we'll be going over will be in that listed there. And there's a whole string of them. Okay? Now, I think after that, you'll see one that says MTH112, Math 112, YouTube videos. Those are videos I've made concerning, in fact, I'm making one right now. Every class I record. Okay? And if you don't see this little circle here with the two lines through it and a timer here, hey, you're not recording. Okay, so I sometimes forget to turn it off. So I'm recording right now, and you can go there. Now, you'll see a whole bunch of videos, more than I've done this term. The ones at the top are from previous terms. If you go, scroll down and down to the bottom, the first one you see there that says syllabus, that's the first video I made last Thursday. We didn't have class Tuesday because of weather, remember? So we had class on Thursday. Nothing worked. We didn't get much done. So Tuesday, nothing worked. We didn't get much done. But the second video says research. That's the research paper. We have finished with the syllabus and then went to research paper. That's all we had time for. Today, we did safety, and we're getting started at 1.4. So you can hear me talk about everything the rest of the class heard. Okay, so you can go to those videos and find out what's going on. You can look ahead to see what's coming up, because those from the earlier times, that's what that is. Okay. Now, when we finish up in here, and I put a new video out there, then I'll take off the one at the top, so there's not that much duplication. There'll be overlap, but not that much duplication. All right. After that, YouTube videos, you'll see some other files. They're web links that either I found or students have told me about that they found useful to the course. So you can go to those if you want to. Okay. So that's how you can catch up anything you missed in the first two classes. All right. We're just getting ready, maybe, to get started on math now. All right. The first part of this class, we talked about safety, so you can go back and hear that if you listen to the first part of today's video. It'll be at the bottom when it gets out there. All right. So, Chapter 1, functions in the graph. And I want to make you recall something here. Remember in the syllabus what it said about this course? This course is the algebra of functions. And that's why we start with Chapter 1, functions in the graphs. And by the way, this book loves graphing. You're going to see a graph on just about every quiz and every test. Maybe not everyone, but I think just about every one. Okay? Be prepared. Okay? 1.4, what better place to start than functions? Okay? You may have hit the beginning of this in Math 100, maybe even 098. You may have had it in high school, but that's where we're going to start here. Functions. Objectives here are to determine whether relations between two variables are functions, and we'll also use the function notation. We'll find domains of function. We'll use functions to model and solve some real-life type problems. And we'll evaluate something called a difference quotient. Okay. So let's get started. Introduction to functions and function notation. Many everyday phenomena involve two quantities that are related to each other by some rule of correspondence. Okay? Let's just take, for instance, my wife's a researcher at UAB, and she researches. A lot of her research focuses on newborns, so she collects a lot of data on newborns from University Hospital and other places as well. And a lot of the things she looks at are things like birth weight, length, age, gender, all these things. Well, pick any two of those. Okay, for instance, let's take a young child, and what if you measured their height and measure their weight in a periodic manner? That would be a relation. Height versus weight. Okay? And over time, as the child grows taller, generally the child picks up weight, right? There may be little setbacks here and there, but that is a function. A relation between two quantities, mathematical quantities. Okay? Some of these are, okay, what we call, this is called a relation. I knew it was in here somewhere. I couldn't see it right in front of me. That's called a relation. Anytime you have a mathematical term for any rule relating two quantities together is called a relation. Okay? There could be some that don't make a lot of sense, like your birth date and your gender. Okay? That's not going to have a very strong relation. It is a relation. Everybody has a birth date and everybody has a gender, okay? So it could be a relation. Might not tell you much, but it could be. In mathematics, equations and formulas often represent these relations, okay? And you probably can think of several now. A equal pi r squared. What's that? Area of a what? Circle, exactly. The radius of the circle corresponds to the area of the circle, right? The larger the radius, the bigger the area. That makes sense. And quite often we use equations and formulas to represent this. Here's another one. The simple interest formula, and I don't know why this slash is here, okay? Simple interest earned on $1,000 for 1 year is related to the annual interest rate. Now this is if it's, and when they say simple interest, they mean you only figure it once a year. It would be the interest earned is the principal there, 1,000, times the interest rate. Now the interest rate, even though we might say it as a percent, we write it as a decimal, okay? Nowadays the interest rate that you get on money saved is minuscule, 0.05% or something like that. I mean, it's just pathetic. The interest rate you pay on your credit cards, still 24% or something like that. That's outrageous. But the interest you earn on savings is pretty poor. But that's the formula. Whatever your rate is, multiply it by your principal, that's what interest you earn. Okay? So, the interest depends on the rate, right? We call this the independent variable because you choose a rate anyway, okay? The interest depends on what rate you're doing. If you find one bank that's 0.5% and the other one's 0.25%, go with the 0.5, okay? Now, that formula, I is equal to IR, 1,000R, represents a special kind of relation that matches each item from one set. Okay, remember we have one set, which is the interest rate. Another set is the amount of interest. Okay, matches each item from one set to exactly one item from a different set. If that's the case, that relation is called a function. Because if you got 0.5%, that's going to be the same interest on that $1,000 now, or next year, or 3 weeks from now. If it's the same R, you're going to get the same interest. Okay? Now, to me, that's sort of abstract in thinking. I like to think of it this way. What if you go down to the bookstore, and there's a line of people there ahead of you, and you happen to have picked up a bag of chips, okay? And the person ahead of you has an identical bag of chips, same company, same everything, and you see they get charged $1.19 for the bag of chips. And then when you go up to the register, you are $1.29. Are you a happy camper? No, because the same input should give you the same output. For any item in the first set, you should get exactly the same amount in the second set. Okay? That's a sort of dumb example, but that's what a function is. That has to be true. So here's your definition. A function from set A, that's your input set, that would be the interest rate here, the item that you're buying, to set B, that would be the interest earned, the amount you pay, whatever that is a relation that assigns to each element X in set A exactly one element Y in set B. The set A is called the domain of the function. That's all the possible values you can choose from. The set B is called, and I used this term earlier, the set of inputs, okay, and of the function F. And the set B, that's the cost, the interest, whatever, is the range, all the possible outputs, okay? That's the definition of a function. For any input, you can only have one output. Now, you could have more than one, you could have two inputs that have the same output, that's fine. But for any input, you can only have one output. Like a bag of chips could be $1.19, but a candy bar could be $1.19 as well. That's okay. But this bag of chips and that bag of chips better have the same value as the output. Now, here is an example. Now, there's lots of ways to express a function. This is called kind of a mapping, okay? Here is a situation. What we have here is the time of day in the afternoon. 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, and 6 o'clock. No special reason why they put them in this order. But this is your domain, the input set. The times of day on the hour between 1 and 6. Those are your inputs. Okay. Over here on the output, we have temperature, of course in degrees Celsius to make it confusing, but it's okay. Degrees Celsius, okay, temperature. Now, let me get an idea here. If we have a thermometer outside in the yard here, and at 1 o'clock in the afternoon, how many temperatures do you think we can read off that thermometer? One! Only one. It's only going to be one temperature at 1 o'clock in the afternoon here on this campus, okay, at one thermometer location, okay? So yeah, there's only one output. For any input, there's one and only one output. Okay, at 1 o'clock it read 9 degrees Celsius. It sounds pretty cold, doesn't it? It's not, okay? 9 degrees Celsius would be about, well, it is pretty chilly, okay? About 47 degrees or something like that, okay? 2 o'clock it's raised to 13 degrees Celsius. At 3 o'clock, it's gone up to 15 degrees Celsius. At 4 o'clock, well, it's still 15 degrees Celsius. Is this still a function? Yeah, because for any input, there's only one output. Okay? It's just that these two inputs give you the same output. That's okay. At 5 o'clock, it dropped to 12 degrees, and at 6 o'clock, it was down to 10 degrees Celsius. That's a function. At any given time of day, there's one and only one temperature. Now, we used all of our input, all the members of the domain. We didn't use all the possible temperatures, and we didn't even list them all, okay? You could have been at some negative temperatures or higher temperatures. This is probably a late fall day down here in the south, okay? Not that cool, but definitely not below freezing, okay? Any questions? That's an example of a function. Now, that's one way to describe it, sort of a mapping illustration. Here's another way you could describe it. Very same function. It's a set. This is a set of ordered pairs. Now, when we say ordered pairs, both words are important. What does a pair mean? Two. The order, it matters which order, okay? And in this one, always the first coordinate is the value out of your domain, the x value. The time, the time of day it happens to be. I would call that t, not x, but that's okay. You can name it anything you want to. The second coordinate is the y value. In this case, was the temperature. I would call that capital T, but that would make it confusing, wouldn't it? Okay? So here's the set we just saw, set of 1 o'clock, 9 degrees Celsius, 2 o'clock, 13 degrees Celsius, 3 o'clock, 15 degrees Celsius, 4 o'clock, 15 degrees Celsius, 5 o'clock, 12 degrees Celsius, 6 o'clock, 10 degrees Celsius. That's listed as a set of ordered pairs. Another way you can express a function. A mapping or a set of ordered pairs. Ordered pairs are important. Independent, dependent. Input, output. Okay? X, Y, usually. Okay? Not always. Now, here's characteristics of a function from set A. What do we call set A? Domain. To set B, the range. Very good. Each element in A must be matched with an element in B. You can't have a time of day here with no temperature, okay? That doesn't make sense. Anytime that you check, there needs to be a temperature, okay? Some elements in B, that's your range, may not be matched with any element in A. We saw that earlier, okay? Back here. These over here we didn't match. Not at those times of day. That's okay in this one, but you need to match all the ones in your domain, okay? That's number 2. Number 3, 2 or more elements in A may be matched to the same element in B. We saw that, didn't we, right here? 3 and 4 o'clock, 15 degrees both times. That's okay. No problem there. But you couldn't have a 2 o'clock at 13 degrees and over here have a 2 o'clock at 15 degrees. That's not going to work, okay? Because at 2 o'clock there can only be one temperature. For this to be a function, okay? Now, and this is the important one that I just mentioned, okay? An element in A, the domain, the input, cannot be matched to 2 different elements in B. Can't happen. That's not a function, that's just a relation, okay? But it's not a function. Okay. If you were to say to me, what's your favorite dessert? And I would say, anything chocolate or apple pie, okay? Preferably apple pie with chocolate ice cream. No, I didn't say that. Okay. But there would be 2 possible outputs for my input. That's not a function. That's a relation. I like them both. In fact, I can't think of many desserts I don't like, unfortunately. Okay. But anyway, that wouldn't be a function. Okay. Now, I mentioned a few ways you can represent functions. Here are 4 common ways. First, verbally. Like I said, a child's height versus birth weight. Okay? Or not birth weight, weight. Okay? That would be one way. Verbally, by a sentence, describes how the input variable is related to the output variable. Okay? Number 2, numerically. Now you can do this as a set of ordered pairs like we just saw, or preferably, y'all remember your T-tables when you were graphing? Okay, yeah, that's a set of ordered pairs. X, Y, X, Y, X, Y. That's numerically. A table or a list of ordered pairs that matches input values to output values. You don't want to cross those up, right? If you do, your graph looks really weird, okay? In fact, you can't even do it. So that's another way. Numerically, either by list of ordered pairs or in some type of table. Okay? Graphically, ooh, yes. Once you got that T-table, then you plotted your points, you have your graph. Okay? That's one way to represent a function. And we'll talk about some very special features of that later. But right now, we'll just do this. On this graph, we almost always put on the horizontal axis the input values. Those are members of the what? Domain, exactly. And on the vertical axis, we put our the range values, the output values. Okay, that's how we represent these. Now, the last way is the way we're going to use mostly, and that's going to be algebraic. I is equal to 1000R, an algebraic expression. Okay, and generally those, not always, but generally those will be functions. We'll run into some examples that are not coming up pretty soon, if I can ever get there. And by the way, I probably should have the book open to the right page. Now, this first section is very long. 1.4 is a very long section, so we're not going to finish it today, obviously. In fact, I'll keep on talking forever, and since I don't have a class after this, I can go on and on and on, okay? So y'all remind me. Don't let me go too far. Okay. To determine whether a relation is a function, you must decide whether each input value is matched with exactly one output value. Now, if you have a huge domain, that's going to be really hard to do. When any input value is matched with two or more output values, the relation is not a function. They've said that a couple of dozen times now. Okay? Now, there are some easier way to do this, but let's do example 1 here. This, by the way, is in your text on page 36. Determine whether the relation represented here represents y as a function of x. So here is the verbal, the sentence. The input value x is the number of representatives from a state. The output value y is the number of senators from the state. And we're talking about at the national level. This is the Congress, congressional delegation. These are your senators. Okay. Is that a function or not? And it is a little tricky. What do you say? Yes, it is. Okay. Why? Say again? Okay. What if we had two states with 10 representatives? How many senators they got? Oh, this is history or political science or something. 2, exactly. If you have 25 representatives, how many senators you got? 2, okay. If you have 43 representatives, how many senators you got? 2. If you have 1 representative, and there are a few states with only 1, 2 senators, okay. Now, no matter what your input value is, you only have 1 output value, and that's 2. That's a special kind of function we call a constant function. The output never deviates. For any one here, you only have 1 there, is 2. That's all you can have is 2. So that one is a function. Now, what if I said it the other way? The input value is the number of senators and the output value is the number of representatives. No way. Not even close, okay? Because everyone has 2 input, and you can have all these different outputs. Yeah, that could be a function. The way it's stated here, that is a function. Okay? Not a very meaningful function, but it is a function. How about this one? Here's a table form. Okay? Is this a function? I can't hear. I'm hard to hear. Huh? Yes. You say it is a function. Oh, I heard a no. Why did you say no?
You have 2 twos.
You have 2 twos here, with different outputs there. Can't have that in a function, okay? You could have the same output here for two different inputs, but you can't have two different outputs for the same input. Not a function. So that one is not a function. Now here's a graph, okay? Oh, let me back up a moment here. What is your domain of this function? B. Not function, relation. What is the domain of B? Yeah. 2, 3, 4, 5. What's the range? Yeah, 1, 5, 8, 10, 11. Okay? You can say them any way you want to. Okay. Now, here's C. Is that a function? What do you think? I heard some yeses here. Why? What is your domain?
1 and -1.
Okay. The domain is your various values on the horizontal axis, and that would be -2, -1, 0, 1, and 2. You see that? Okay. Now, what's your range? -1. Actually, it can be anything, but the values we use here are -1, 0, 3. Those are the only values we use. Okay? Now, is that, and y'all said it was a function. Why? For any one input, you have only one output. Right? It is a function. Now, when you do a graph like this, I'm jumping ahead here, but no extra charge on this. Graphs are really easy to check. Anyone know the test we use? Vertical line test, exactly. If you draw a vertical line through any one of those points, they only intersect once. Whereas if you graph this one and you draw a vertical line through 2, you'd have an intersection at 10 and 11. So you see, not a function. Make sense? Okay. So this indeed is a function. And you already identified the domain and range. Y'all are good. Now, the first one, the verbal description, does describe a function of x. Regardless of the value of x, the value of y is always 2. Okay? That's called the constant function. Never deviates. Okay? The B one did not describe y as a function of x because the input value 2 had two different output values, 110, 111. Not a function. Make sense? Any questions? Okay, and the third one does describe y as a function of x. Each input value, -2, -1, 0, 1, and 2, only had exactly one output value. 3, 0, -1, 0, 3. Only one. Make sense? Good deal. Now, representing functions by sets of ordered pairs is common in a branch of mathematics we call discrete mathematics. That doesn't mean that you're quiet about it. No, discrete mathematics means you can count the possible answers. Okay? Countable. Okay, discrete mathematics. In algebra, however, it's more common to represent functions by equations or formulas involving two variables, and these could be infinite. Okay? For instance, y is equal to x squared. Okay? You think that's a function or not? You say yes. Why? I'd say, and I feel like a cheerleader now, I say, give me an x. Say again? Give me an x, a value. Say it. 3? Is that what you said? I can't hear. 3? What would be your y? Oh, 2? Well, if you gave me a 2, what would the y be? 4. You only get one answer, right? If you give me an x, it's only going to produce one y. No matter what x you give me. You can't give me an x value that's going to give you more than one y. Not in that. So y is a function of x. So that represents the variable y as a function of the variable x. Now, I'm going to ask you sort of a question ahead of what's your domain of this function? Say again? Okay, the line. The horizontal axis? It's the what? No, the y. No, the y is your range. Okay, the x is your, I'm sorry, I don't hear well. Okay, the x is your input. Okay, what's the domain? What value can you put in there? Any real number in the world. Negative 4,585,816.3. You can put that in and you can square it. Okay, or 7 pi. You could put that in and square it. Okay, any number in the world. What's the range of that function? Say again? Anything? Can you get negative 1 as an answer? What number could you put in for x to give you negative 1 as an answer? It is not 1. Anytime you square a real number, remember we said all real numbers, square a real number is always non-negative. You could say positive, except when you square 0, you get 0. That's neither positive or negative. But it's always non-negative. So your range will be from 0 to positive infinity. Your domain, negative infinity to positive infinity. All real numbers for your domain, only the positive or non-negative real numbers for your range. Okay? Now in this equation, because what did I ask? Give me an x. You have to know the x before you can figure out the y. So y depends on x. So x is independent. You can choose any x in the world. I didn't say you had any restrictions on x. I said, give me an x. So that's the independent variable. Y is called the dependent variable. Your domain is a set of all independent variables. Your range is a set of all dependent variables. Make sense? All right. The domain of the function is a set of all values taken on by the independent variable x. The range of the function is a set of all values taken on by the dependent variable y. What I just said. I forgot the slide is in here. Okay? Any questions? All right. When using an equation to represent a function, it is convenient to name the function for easy reference. Now, you could name it Sue or Bob or Fred, but that's not really all that easy. So we usually come up with a different way of naming functions. For example, if you know this equation, y is equal to 1 minus x squared. It describes y as a function of x. Give me an x, any x in the world, I can give you a y. Okay? So y is a function of x. So, mathematicians being as creative as they are, came up with what will we name this function? Function. Function. How about naming it f? Okay? For function, okay? Pretty simple name, huh? Mathematicians are very creative, okay? Then you can use the following notation. If your input variable is x, right there, that's what you get to choose. The output variable, the variable is y, but the function is f of x. F assigns to x. Here's what. A way to think of this function f. When I was in first quarter freshman at Georgia Tech, in my first calculus class ever in my life, I never even had pre-calculus, and I was in a calculus class, but the professor gave this example that stuck with me. He said, think of your function like a black box. Okay, you put something into the box, you turn the crank, and something else comes out. That's what he said of the function. And I, being growing up on a farm in Georgia, I thought, oh, grinding sausage. Okay, that's what I thought. Because when I was very young, and my father was a farmer, and we raised pigs and chickens and cows and everything else, but the pigs we usually slaughtered ourselves. Okay? And when we slaughtered the pigs, I always tried to do it the coldest day of the year. Okay? And when they did, it was an all-day affair. I mean, started very early in the morning and then went through, and I won't go into all the gory details, and it was some of it pretty gory. But when you finally got the meat in the house, my father would be cutting it into pork chops and pork roast and stuff, but there'd always be scraps. And he'd have a pile of scraps that would be going there. Things he cut off that had a little bit of red meat on it, he'd be putting in a pile. And that pile, as he cut and did, grew and grew. And finally, at the end of the day, when he had packaged all the pork chops and pork roast and anything else, that pile of scraps, we'd set up the sausage grinder. and you did it to the table here, and this was my job. I would turn the crank on the sausage grinder, okay? And they would put in the scraps, the pieces of meat, the little strivers or whatever. Sometimes some gristle and fat went in, but as little as possible. And then the spices, the herbs, the sage, and all the other things that make it taste good, and out would come the sausage, okay? The input, the output. The function was the meat grinder, okay? When he did that illustration on the board, I thought that, and that's how I've always thought of functions since then. You have input, you operate it on with the function. The function tells you what to do. This function says, give me an x, I'm going to square the x, and then subtract that result from 1. That will give you the answer. That's what the function is telling you to do. Take the input, square it, subtract it from 1. That's what that function says to do. That's the sausage grinder. Okay? Here's the equation. F of x is equal to 1 minus x squared. Now, how does that relate to this? Do they look similar? What could you say about it, looking at those two equations? Okay? Well, not the same thing. This says y, this says f of x. So what could you conclude? If they're both the same thing here, then this means that y is equal to f of x. If you remember that in this course, that's going to be the most important single fact to remember. Y is equal to f of x. I mean, it sounds so simple, but that's going to give it to you. Now, sometimes we'll use different variables and stuff like this, but the principle is still the same. Whatever your deep in the variable is, that's going to be your function. Okay? Because the other side is the same. That operates on the x. Okay. The symbol f of x is read as a value of f at x. Okay? If you want to put a lot of words into it, you can do that. The value of that function when you have the input value of x, or simply f of x. Okay? Make the parentheses say of. F of x. That symbol f of x corresponds to the y value. Y is equal to f of x. There it is in bold print. Not in bold print, but in print. Okay? That corresponds to the y value for a given x, so you can write y is equal to f of x. Remember that, and you've got most of this course not, really. Keep in mind that f is the name of the function, clever name, f, and f of x is the value of the function when you plug in an x. Okay? For instance, here's a function. F of x is equal, and we use f of x for all sorts of functions. You don't have to come up with a new name for every function. So f of x equals 3 minus 2x. Okay? What is f of minus 1? Okay? Yes. Try again. 5. Okay? Because when you plug in the minus 1 instead of the x, plug it in here. 3 minus 2 times minus 1 is, remember your rules of order of operation? Please excuse my dear Aunt Sally. I don't know what she did, but please excuse her. She can't help herself, okay? So, the multiplication is done before the adding and subtracting. My dear comes before Aunt Sally. Okay. So, that's it. 5. Okay. How about f of 0? I love this one. Is what? 3. Exactly. Plug a 0 in for x. See, whatever is in here, you replace what's here with that. Okay. And how about f of 2? Is what? Yes. Very good. Y'all are good at this. Okay. To find those values, you substitute what takes the place of the x here, you make it take the place of the x there. That's all you do for evaluating functions. We're just beginning to have fun. Okay. So, where in the world were we? You know, we missed example 2. So, when we come back next time, we're going to start at example 2. And by the way, There's a handsome-looking character in your book. I don't know if you noticed him. Leonard Euler. My word, what a good-looking guy he is. He's a Swiss mathematician. Y'all don't have your books yet, do you? Okay. One of the most prolific and productive mathematicians in history, and one of his biggest things, he did many wonderful things. He came up with this alpha of x idea. He's the one we blame it on. I mean, he's the one that we celebrate. Okay. Now, he was so prolific, he lost the sight of one eye, he kept writing papers. Even when he lost the sight of both eyes, he could do it all in his head. He continued writing papers. He had somebody else write them for him, and he would listen to them and proof them in his brain. He was incredible. So we'll begin next time at example 2. Homework exercises. If you turn over to page, this is a long section, like I said, 44, I think you can do any of the odds 5 through either 5 or 7. Now remember what I said about these homework exercises? Number 1, the answers for the odds are in the back of the book. That's why I give you the odds. But if you can't get those answers in the back of the book and you can't figure out why, then look at the top of the page here. See calcchat.com for tutorial help and work out solutions to odd number problem exercises. Yes? The page is 44, and do either 5 or 7. They're both at CalcChat, but 7 is in red. And 7 also has this the set of exercises has this QR code. If you take your cell phone and do that thing, if you have a QR code reader on your phone, most of you do, you can see a tutorial, an interactive workout of that problem. I can't think of the right name for it. Okay, you can also do number 9. It's at CalcChat. Okay. Hold off on 11 until we do example 2. So not mandatory homework. Sorry, yes. Okay. On page 44, either 5 or 7 or both, and number 9. It's not much homework, but you can probably do it in just a few minutes. Okay? We'll get along a lot faster next time. Okay. Good deal, folks. Looks like a good class. Appreciate your being here. I'm sorry? Not yet. I'm going to try to get in touch with them this morning.
I can't do the homework without it.
You can't. Nothing. Okay. Can you take a picture with your phone? Okay. If you want to do that, you can do that. Either somebody else's or mine.
Did you ever take up the topic paper?
I'm sorry?
The topic paper that you told us to work on?
Okay, yeah, if you got them, I'll take them. You got it? Anyone got topics for your paper? I'll take them.
I'm in the way. That's all we have to do.
Good. Yeah, that's it. Thank you.
It's actually about the science. For like our piece of paper that we can like write something. Can we type something?
That what?
Can we type something?
Absolutely. Absolutely. Yeah.
So is the book? Is it also on Cengage?
Yeah. Okay. If you do the Cengage Unlimited, you can get the ebook, and for an additional $8, something like that, you can get a paper copy. So that's just a rental. You have to turn it in at the end of the term. Yeah. Sure. Okay. Here's my book. Anyone who wants to take a picture. It's all on this page right here, 44. It's just these right here. Okay. Okay. All right. Good deal. Thank you.